right, welcome back. So last time we talked about what waves are and the two main types of waves. And what we're going to do now is talk about the types of wave motion and their parts. So like I said, this part can get a little bit confusing because people tend to use terminology in a very confusing way. I would say wrong, but whatever. So these are, like we said last time, two types of waves, mechanical and electromagnetic. The only difference is mechanical waves need a medium because they are the medium, right? Like ocean waves are the ocean, sound waves are the material that they're vibrating. Whereas electromagnetic waves are kind of their own thing. They kind of are their own medium. Like, they are electric and magnetic fields. So electric and magnetic fields can exist anywhere, in a vacuum and, matter, whatever. It's just the oscillating of those fields. So they kind of move through the medium instead and kind of push it out of the way. Is a way that you can kind of think about it. It's a very, very oversimplified way to think about it, but it's kind of helpful, right? Mechanical waves are the medium, whereas electromagnetic waves move through it. But what we're going to be focusing on today is the types of ways they can oscillate. There's two main ways. I mean, there's a third kind of combination way, but we'll just talk about the two big ones. And those two ways are called transverse and longitudinal. Right, so mechanical waves, they can really oscillate. Like some mechanical waves are transverse, some waves are longitudinal. And see, I just did it there myself, right? Transverse waves, longitudinal waves. And you'll hear that vocabulary used a lot, very often. But really, that's not a type of wave. It's really just a type of oscillation, which you'll see in the next part. Now, some mechanical waves are travel transversely. Some mechanical waves travel longitudinally. But electromagnetic waves only travel transversely. And we'll talk about what those mean. That probably doesn't mean a whole lot to you right now at this second, but hopefully by the end of this video, that'll make a lot more sense. But again, the big thing I want to clarify here is that these are types of waves, mechanical waves, electromagnetic waves, and these are types of motions, transverse and longitudinal. So we'll start off with the one that's, when you think of a wave, is probably what you think of most, and that is transverse motion. And transverse motion kind of looks like this. All right, so it'll go back and forth like that as the energy goes across the screen here. So the oscillation is up and down. Now, if we were in class together, we would be doing this with a giant slinky that stretches across 2 lab tables. But alas, here we are, so we have this. So you'll notice that the oscillation is up and down, but the energy travels across your screen. So up and down, left and right. Oh my gosh, let me see if I can do this. Yeah, kinda. So up and down versus left and right, those angles would be perpendicular. Yeah, and that's really what defines transverse motion. The oscillation is perpendicular to the propagation, which is a fancy way of saying it goes up and down, energy goes left and right. Kind of like this.
Okay, that could be better.
And this happens every time. Cool.
Yeah,
So you can
that's
see
better.
here, I'm going to turn that down a little bit. There we go. So with this giant slinky, the oscillation is going left and up and down, and the energy is going left to right. Now, the key thing here, and this is kind of what we talked about before. When I say energy, you say... I just messed that up. When I say wave, you say... energy. Yeah. So waves are energy. Very important here. If we take a look at this, in the middle of this slinky here, I'm going to pause it, is a little ribbon that's tied here. And I want you to pay special attention to this ribbon while I unpause it here. What do you notice about it? Yeah, it's not moving down the line. It's just oscillating up and down. It looks like the slinky's being sent down this way. But it's not. And that's a key here. Waves do not transfer matter. They transfer energy. They can oscillate the matter, right? They can shake it back and forth, but they do not propagate the matter. The matter does not get moved because of the wave energy. Right? And that's kind of misleading based on the animation we just saw here, right? So it looks like, a material is moving and just leaving its tail behind. But no, this is just signifying the energy, right? If there was a long string here, what the appearing of the line here, appearing of the line is showing you is which way the energy is traveling. Because there was no energy in the string, before it was being oscillated. Just like with the spring here, there is no energy in the spring unless we start oscillating it like this. At least wave energy, that is. So it shakes up and down like that. So one key thing here, and this is true for any kind of energy motion, transverse, longitudinal, like cyclical, whatever. We do not transfer matter. We don't transfer material, we transfer energy. And again, like I'd say at this point, MCAS always tries to trick you on this every single year with a question about it. However, we're not taking MCAS, but still, it's very important. Like, it's a fundamental thing about waves. Waves are not matter. Waves are just energy. So let's get down into the different parts of transverse motion. So as things travel transversely, we can label parts of the wave. But if you want an official textbook definition, transverse motion means that the oscillation is perpendicular to the energy propagation. Here, right? So the oscillation is up and down like this, while the energy is being propagated from left to right. Those two directions are perpendicular. And that's what makes it transverse. Now, another thing we're going to talk about is this normal. Now, we know that we've used the word normal before when we talked about, forces. And the normal force was the force that did what now? Yeah, acted perpendicularly to the surface. Now, we're going to use normal in a different way now. We're going to use it in a more traditional way. The normal here is like the midpoint of the oscillation. It's the normal resting state would be if there were no energy being transferred through the waves. So in this case, it would represent by just a straight line, like if we just held the slinky before we started oscillating it, like that. Yes, I'm dancing. You're welcome. And it's important that we define that because some of these other terms that we're going to be talking about are going to be referenced from the normal there. So the first thing we're going to label are the tops and bottoms of the waves. Right, so as this wave travels transversely, it creates these top little peaks up here and these bottom little valleys. Peaks and valleys is sometimes what they're called, but their official names, as determined by scientists long ago, because why not, would be crests. So the crests is kind of the fourth motion, right? We talk about back and forth, fourth being kind of like positive, back being like negative. So these are all the tops of the wave. So you can almost think of this as like an XY axis. Right, where the normal represents the x-axis, and this is the y-axis. So the highest point, the highest positive point of transverse motion of a wave traveling transversely, we would call the crests. So each one of these little things up here is a crest. Where the bottoms would be those valleys, or as they like to call them, troughs. Like a pig trough on a farm. It's like a trough, a little thing that they hold, they put the food in, they eat, trough. I don't know, valley would have been, I don't know, whatever, words, rose by any other name, as you hear me say a lot. But they're the back, they're the most negative part from normal. And again, those are all the little bottom parts there. So with transverse motion, you got crests and troughs, labeling the maximum and minimum of the oscillation there. So they're kind of like the most furthest away from the normal that you can get. And that's it for transverse motion. That's all it is. Just, oscillate perpendicular to the propagation. So the opposite of perpendicular would be, this parallel. Now this one's a little bit trippy to watch, but instead of oscillating it up and down, you're gonna, in the direction of the energy, you're gonna oscillate it. So I like to call this the squishies and stretchies. That's not their official names. They're just much more fun to say. But that's essentially what you're doing. So instead of oscillating the material up and down, you're squishing it and stretching it. This is how sound waves travel. Like we talked about, right? It's like the compression of air and the stretching out of the air. So all sound waves travel longitudinally, which is weird because we often see them drawn transversely like this. But we'll get into that next week when we talk about sound waves in more particular. But yeah. So here is an example of it on a slinky. And you'll see that as it goes, you kind of push it. And what you get is this area of compression that goes forth. And this one's even more of an optical illusion, right? It looks like something is straight up traveling right down the line. But if you pay attention to these strings here, you'll see that that material does not go anywhere. It just kind of gets stretched, and then it comes back this way. And what you end up with are these kind of sections where it's squished together and this section where it's stretched out. or as that's called, squishies and stretchies, instead of crests and troughs. That is not their official name. We'll talk about their official name in a second. But you can see here, if we pause it, right, so this section here is all compressed together, right? You can see the normal state of it, and this section here is a little bit more stretched out. So with the transverse motion, it's kind of easy to tell the crests and troughs because they're like, they're just opposites of each other. These squishies and stretchies, or compressions and rarefactions, as we'll define in a second, are harder to see. The compression's easy. It's easy to see the squished up part. But the rarefaction just takes up so much space here. It's kind of hard to see where it begins and ends. But that's just kind of how it works. The compression, the oscillation, is going to be parallel to the direction of that energy there. As we go across like that. So let's put some definitions to it. Longitudinal motion, like we just said, the oscillation is parallel to the energy propagation. So meaning we're oscillating the material in the same direction that the energy is going. Oscillating it this way, energy is going this way. Or, because it's a camera and it's backwards, oscillating this way and energy is going that way. Here it doesn't really look like it's kind of going anywhere. That's just the best I could do with the animation. But for PowerPoint, I think that's pretty darn good. But as you saw with the other one, right, it's just that when you send out a pulse, it just travels down the line. And so in a kind of frozen state, like we said, the squishies and stretchies are actually called compressions and rarefactions. And this is going to be nice and confusing because there's also a term we're going to talk about called refraction, which has nothing to do with rarefactions. So, science. But again, the key thing here is that transfers energy, not material, not matter. We can go back to that for a second, and we can kind of see in the Slinky video that the matter is not traveling down the line. Right? We watch this compression moves, but none of these sections. The section, this part here moves forward, but then it also comes right back to where it was. Right? This one here, we'll use this one as an example. We can see it was there. It got squished. So it's gone. Let me keep my mouse there. And it got stretched out, but it comes right, hopefully, back to where it started from. Bam! Science. Or as somebody said, boom science, let's go. Or boom magic, let's go. Right? Anyway, it's an inside joke. You'll understand later. So yeah, longitudinal motion, parallel to the propagation. The oscillation, parallel to the propagation. There's a lot of rhyming in this one. It's a lot of fun. And instead of crests and troughs, tops and bottoms, we have compressions and rarefactions, squishies and stretchies. And like we talked about with sound waves, it's actually like the particles, the air particles themselves are getting compressed and stretched out. And this is kind of what a sound wave would look like, right? So the compression here is the squished part of the wave as it gets sent out, right? Bam, 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 bam. Gets squished. But then as that's getting squished, other parts are getting kind of stretched out. The kind of areas where there's less material and less molecules. And those are the rarefactions. Those little sections there, where the material gets stretched out. And that's pretty much it. That's all there is to it. I know the first video was crazy long, but this one the rest of them will hopefully be nice little shorter sections, little subsections here. So what questions do you have? How do ocean waves travel? Kind of both. They kind of like go up and down and around in a circle. So they've kind of got transverse and longitudinal in the same kind of motion. How do earthquake waves travel? Both. There's two types. There's some that are kind of compression waves, and there's some that are kind of transverse waves. I forget what they call them, but S waves and P waves, I believe, are their terms. But yeah, so think about it. What questions, connections do you have? Please consider posting them to the discussion board. See you next time.